Okay, so last time we talked about a bunch of stuff. Now we're going on a slight detour, a rather large detour actually. We're going to ask today, why is the sky blue? Because I can't do a physics course and not teach you why the sky is blue. Probably a lot of you already know the answer to this, but it does have a little bit of relevance to what we're talking about. Uh, the sky is blue because of something called Rayleigh scattering. Okay. So in space, you have the sun, right? And the sun emits light at the Earth, okay? And light comes in a spectrum, and it starts with low wavelength and it gradually becomes higher wavelength, okay? So here, this part is violet. That's what we call it in English, this colour. And this part is red. And so then that's why this part of the spectrum goes on to infrared, and this part goes on to ultraviolet, right? And this part, you can see, has more energy. It's moving more in the same amount of time. And that's why ultraviolet hurts you and infrared does not. And then if you get even closer, the gamma rays can give you cancer, and then radio waves will pass through entire buildings and not even hit anything. And that's the key there, is that this white light that we see, white is what are the cones in our eyes see. We've got red, blue, and green cones. And when you've got enough red light, so that's these long wavelengths, and you've got green wavelengths, this is going to look a bit like DNA here. Right? That looks like white to the human eye. But when it enters Earth, it hits the atmosphere. And you've got all these particles in the atmosphere. And if you imagine there's some blue light that's going like this, and there's some red light that's going like this, right? Well, if you have a bunch of particles in your atmosphere, then the blue one is much more likely to hit these particles, right? And when it does, when the blue light hits these particles, it flies off in different directions. Meanwhile, on average, the red light just passes through because it doesn't even connect, right? So your eye looks in the sky and sees all of these blue light, like these blue particles that are being reflected, but it doesn't see the red ones because they're going right through. And the only time it does see red ones is, say you've got a cloud in the sky, okay? Now, clouds are much thicker and denser, and there's much more particles inside them, and the particles are larger, and so the red light does get reflected as well. So when you look at a cloud, you're seeing green light reflected, you're seeing red light and blue light. So that's why when you look in the air and see dust or clouds, they're white, because you're just seeing the sunlight as it should be. But the sky looks blue because you're only seeing these sections. And just as a quick thing, like most of the light from the sun is sort of in this range. If this is violet, and also your cones are more finely tuned to see blue. That's why we see blue and not violet, because these sort of square at each other and it becomes more like this. So you're going to see way more of this blue band. So anyway, what has this got to do with anything? Well, if you imagine you're a fish, okay, and you're looking up, well, the fish knows they're in the ocean, right? Because they can see. It's the same thing, right? They can see color bouncing off, and if you have a box that's dropping through the ocean, well, we can see with our naked eye that there's water in the way, right? And the box tries to move down, but there's water particles everywhere. And if this has a mass of m, then the force down is mg. So this thing will drag the particles underneath it and pull them down. And each one of these teensy tiny particles is experiencing some force as the box pulls them down. And as we know from Newton's third law, every action has an equal and opposite reaction. So every little particle that this box pulls down also pushes up on the box. Right. Now, the difference is we live on a planet and we essentially live at the bottom of a giant ocean of air and nitrogen and carbon dioxide. You just can't see it. But it's like being on the surface. There's a giant ocean around us. We just can't see it. It's everywhere. We're literally at the bottom of a huge fluid, like the sea. We're just on the surface, like a deep sea diver is on the surface of the Mariana Trench. We're on the surface of this huge, huge ocean. Now, I say huge, it's actually relative to the radius of Earth. It's about as thick as an apple peel. It's quite thin indeed. In fact, it's worryingly thin. But so the thing is that there's this fluid all around us, right? And so when you drop a box out of an aeroplane, that also will drag down all these air particles. And that's why at the top of this ocean, all our helium balloons, they will fly up, and they sit on the top of this ocean. Much like a boat sits on the top of the sea, a hot air balloon will sit up here, high in the, it's floating up on top of this ocean. Okay? Not all the way up there, but you get the point. Right. And we have shown that the value of this is equal to, we'll call it F. We'll just say F for now. We can say FD, like F drag. Is equal to minus C times V minus D times V squared. Okay, so it's based on, and this V is the relative velocity. Now, we're going to go more into relativity later, but just think of it this way. If you have a fan, okay, and the fan is blowing wind, right, then even though you might not even be moving, you're going to experience the drag of that wind on you. Okay. But in general, I mean, we do that in video games, but in general, when we're talking about drag, like Unity has a drag slider, right? And when we're talking about that, we're talking about these quantities. Now, it turns out for liquids, so, you got water, honey, magma, right? C is much greater than D. And for gases, D is much greater than C. Now, one trick we do in physics a lot is say, hey, sine theta equals theta when theta is less than 0.1. If you look this up yourself, I mean, you can just put in a calculator, put, sine 0.001 in, and you'll see that it's about equal to, it's like 0.0999, something like that. And the lower you go, right, the more it just becomes equal. right? So in physics, we're happy to work with approximations because nothing's perfect, right? Electrostatic forces are so variable that if something is a good approximation, then that's good enough. So when we look at this formula and we say that for liquids, while C is much greater than D, then what we can see is, let's imagine for a second, let's look at this force again. Right? This C, let's say for a liquid, typically things are moving slowly through liquids, right? We're not often moving fast in a liquid. Most of the time, you're just wading through. So V is going to be small most of the time. So let's say our V is 0.1, and let's say C is 100 and D is 1. Then if you look here, minus 100 times 0.1, right, is minus 10. Okay. Then this is minus 1 times 0.01 squared, which is 0.01. Right, so this is just 0.01. So you can see here that this FD will be equal to minus 10.01. So we can essentially say that for this, for a fluid, this doesn't even matter. It's so small that it's just irrelevant. It's barely going to affect your simulation at all. And we can say, likewise, so that's for liquids. For gases, we can say, okay, V is, this time, if you follow through the air, if you're a skydiver, you're much more likely to be going faster. So let's just say you're moving 30, and this time D is 100, and C is 1. Well, minus 1 times 30 is minus 30. 100 times 30 squared, is 900 times 100, so 90,000. So suddenly your F is minus 90,030. So again, this term doesn't matter when we're looking at air resistance. So this is all we care about when we're talking about drag in air. And we'll come back to this one day in the future, right? But right now we're talking about air resistance because that's the one we experience most in games, not water. Because most of the time you're walking around the air, right? Okay, so we've determined that this drag force is equal to CD, right? This is just the drag constant, okay, times by rho. This is not a P, it's a rho, Greek rho, the density, times the cross-sectional area times the V squared over 2. So that's a lot of stuff, right? Now this CD has all sorts of things inside it. It has like say you have something that's shaped more like this or something that's shaped more like this. These are going to experience drag differently, right? They're going to get streamlined. This one is just going to capture lots of air. This one's really streamlined, maybe. Okay. Well, probably actually this one's better. So this CD is just a magic number. And there's no way of figuring this out with physics. We just measure it and with experiments and say what it is. So the rho and the A, right, this is density. So that's the density of the fluid, right? But this also includes the material. Let's look for a sec at this, right? This is a Toblerone. And let's say your Toblerone is falling. But this thing has a cross-sectional area of A. Right. And this one is falling like this. This has a cross-sectional area of this A, right? So what this A means is that because this one, there's more surface touching the particles, you know, there's more surface touching the wind. I mean, less. There's less here and more here, you see. This one's dragging more particles, right? Then this one is going to experience more drag than this one. And in fact, just because of something that we may or may not get into in this course, inertia, right? This thing is not very stable because it's got all this mass up here, whereas the center of mass is here. So typically, particles will bop this over, and it will end up looking like this anyway. If you throw a Toblerone out of a plane, it will probably end up in this orientation. But you can see that, say we have here a box, and it has a length d, and it has a height d. Well, this surface area is A, it's d squared. And then the volume of this thing is another d, so it's d, you know, it's d squared times d. Or let's say you have a circle here, and this area is pi r squared. Well, to make it into a volume, we just times it by d again, right? Like this height. And even when you've got a sphere, you know, it's pi r squared for the area, right here. But then the volume is 4/3 pi r cubed. You can see that this is a function of, we're multiplying it by d again, and some constant. And what we know about mass is that mass is volume times density, right? So if we can estimate, because we don't care about precise things in a video game, right? In a video game, we're not really bothered about whether if your cube is falling this way round, we don't really care that there's more surface area than if it's falling this way around. We just want one drag number because it's neater and nicer. So when we're talking about strictly video games, it's not in physics in general, we can say that, well, the mass is essentially, you know, the area times the density times some depth, you know? Okay, so the drag formula is not, we don't actually teach it in physics because it's an experimentally proven formula. But if you imagine, right, you have a sheet of steel, right, versus a sheet of paper, and they're the exact same width. Well, the reason that the steel is going to experience less air resistance than the paper is because the steel has a higher mass. You're just going to have to take all of this with a grain of salt because this is not how air works in the real world, but it's how we model it because it's our best estimate and it's the easiest way of doing things. But we can see, it's a good question though. We can see that, you know, you've got all these things like CD, you've got the distance, all of this. All of this is stuff we don't care about because they don't change. So all of the density of the substance itself, all of this, it all gets eaten into a constant, and we can call that constant B, right? And then we still have the mass. It's clearly, right, m times v squared, right? So we know, clearly, we know intuitively that a heavier object, right, will experience less air resistance than a thin object because it's just thicker. It's hitting more particles, right? So this, it's got more inertia as well. So we end up with this formula, mbv squared, which is not, again, it's not an exact science, but it's what we use in video games. Now, interestingly, okay, first of all, let's talk about this, right? One thing we didn't get into when we did Newton's first law is this idea of like static equilibrium, and that is if you have an object and there's a spring here and there's a spring here. Wait, that's a bad drawing. There's a spring here and a spring here, and they're all equally pulling it in these three directions, and they're perfectly, this is 60 degrees, this is 60 degrees, this is 60 degrees. Then this object, it's as if there is no force on it, because the vertical forces all balance out and the horizontal forces all balance out. So this, we can say that this isn't experiencing any forces. Obviously it is, but it's as if it isn't. That's how we model it. So if we have this mg down, right, then we now have this mbv squared up. Okay. And so we can say that overall the F, the force on this object, equals ma, right, equals, and we'll just say g is down, so it's mbv squared minus mg. Okay, now we can just cancel these and say that the acceleration, the dv by dt, equals bv squared minus g. Right? Now, we do not say this in video games. I don't know when this started, but the convention is we actually just say bv minus g. So when you're in a video game, your character, it's essentially more like they're wading through water or jelly, because as we said before, remember that F was equal to, CV minus dv squared. Well, we actually model air resistance linearly in video games. So it's like the air in video games is water. Well, in most games anyway, especially in platformers. Unity's drag does this. Okay, but the default drag. You could do your realistic, accurate physics engine, which wouldn't do any of this. But here's the thing, when we do model, we typically don't care, right? So again, so like when we, do you know what, in Unity, when you're inspector, it just says drag, right? Unity does not care if your square is like this, or your square is like this, or your object is a circle collider, or, it doesn't actually bother with any of this. You'll find that the drag that we use in Unreal Engine, Unity Engine, and something and everything, it's just easier to just use this idea of it's just a liquid. And in fact, this is known as a damping force. Actually, that's why I chose B. We'll come back to this when we go to springs. But it's not actually drag. It's not how drag works in real life. But this is just what we do in video games. Now, if you really want to get into the nitty-gritty of it, you can go on. There are lots of resources out there, and you can, if you just Google drag force formula, then you'll find CD, how CD is made up, all of the different shapes, and how this might be like a 2.4, and this might be like a 1.2 or something, and like, if you were really hell-bent on making a perfectly accurate physics simulation, you could go and find this stuff. I'm not expecting you to do that. Okay. But obviously, I'm not saying you should never do this. If you want to do, you can do whatever you want. It's your game when you make video games. If you want a perfectly accurate drag representation, then go for it. But it would take a long time, and it's a lot of work. Even just working out the bounds of like, where is the air on this? Because if you imagine, like, if this thing is moving in this direction, then the air resistance is in this direction. So now, you're looking at this surface. Whereas if it's falling straight down, you're looking at this surface. So it's almost like a shadow, it's getting depending on where you're going, it's getting cast in a different direction, and you'd have to look at the bounding box and figure out how curved it is. It would just be so much work that this would be an entire project on itself. It'd take you like a year, maybe. Well, maybe not. But it would be a huge undergoing, and you may never be able to do it well because, you know, if you're looking at meshes, it's actually quite a difficult problem in physics, like how shapes, you know, if you've got squares, that's fine, but if you have like a mesh that looks like this, then suddenly, like, how are you going to say how much surface area this has? Raycasting? Which would be a ton of work, or you'd have to just mathematically work it out. It would be a ton of work, and that's why we don't do it. And presumably in the beginning, when you were talking about the days of like old video games or like even just Doom, you don't want to be working out squared. Back then the computers weren't as fast, so you wouldn't want to square things when you can just do it linearly. So for us, it's enough to say that, you know, v of, you know, n plus 1 is equal to vn plus g minus bv times dt. Okay, so that's your fixed delta time. This is your velocity the frame before. This is, you know, your velocity g minus bv. So let's talk about terminal velocity. I'm sorry as well that that's the reality of the situation, is that it's not, you know, in physics you tend to, we've got nice formulas for things like, oh, gravity, it just works, but drag, it doesn't just work. So we just make approximations. It's like it's more like engineering drag. You know, they don't have an exact science for how a building moves. They just say, oh, it's within this range. But if you imagine, you know, you've got your object, it's got a force of mg, so it's got an acceleration of g. It's got this up here. We'll call it bv squared for now, right? Because it's more like reality. This force, you know, this is uniform acceleration. It's just the graph of y equals x squared, right? Because of, you know, s equals ut plus half at squared. We'll come back to that at some point. But so you have this, and this is like a gravity. If you imagine this bv squared, at the beginning, this force is 0 because your velocity is 0, right? And then as you accelerate, this bv squared is going to get higher, right? So you're going to have this force in the opposite direction, and eventually, I mean, it's not exactly like this, but eventually they're going to cancel each other out. So you can see that at some point, v is going to be root g over b. If you just keep adding to it and adding to it, you're going to reach this point, right? Now, and this is just an arbitrary number, right? So this, you're going to have your g down, and then up, you're going to have b times this squared, v squared, so, you know, v squared is g over b. B times g over b, these b's will cancel, and you're eventually going to end up with, you know, this force up is going to be mg, and this force down is going to be mg. And now, hey, we're in equilibrium, and that means we are falling at terminal velocity, which means our velocity is not going up. We're not accelerating anymore. We can't. So if you imagine you've got your velocity here, it's going to look like this, right? You're going to start, you've got uniform acceleration from gravity, and then eventually it just ends up like this and goes horizontal. And in fact, let me try and make a nice, let me go to the pen tool so you can see that this actually ends up like completely horizontal at some point, right? Well, if you imagine an object, when you integrate this line, the object's going to go like this, right? The displacement. So this is a position now. We're going to draw what the position looks like. Well, the position's going to accelerate, right? But then once we hit here, because the velocity isn't changing, it's a straight line. Okay, once we reach a certain point. So from this point, you've now reached your terminal velocity. And from now on, you don't accelerate at all. Okay. How are we for time, by the way? Oh, damn. Okay. Well, we'll go into the simulation. Maybe we'll just catch up a bit on this tomorrow as well. Because I've probably not got enough time to put you through. We're supposed to be finishing in like a minute, right? So I can't really teach you this next whole section. Okay, well... Oh, we got... Do we? Okay, we'll do it. We'll go. Right. So, right here, I've got this water. And, okay. I wish I had more time. Where's my pen gone as well? Okay, it's gonna... Everything's just going wrong today. Right. Well, we probably will end up splitting this into... I'll just cover the start of it tomorrow. But we'll do most of it now. So if you see here, you know, you've got some... Unity is going to resolve this itself. It's going to say that if you use add force, right, and you use force mode velocity, then what it does is it does it all in one step. It adds all the forces together and uses that. So it's going to check this force upwards of like, okay, this is BV times M, right? And this one down is G, mg, right? So then it's going to say, okay, it's going to divide the mass on its own, and it's going to say, okay, we just have, or we'll say minus. You know, we have bv minus g, 0, and this is the force that it's then going to apply in one step. So I wanted to run through a kind of calculation of that, but okay. One thing I'll say is that there's a lazy way of doing drag. Okay. There's two ways of doing drag, really. One way is you can just do it in 2 steps. You can do it how I just said there, with it, you know, it's a force and it resolves everything at once, right? Or you can do it like this. You can do your first step is like V plus equals G, and this is approximate. It doesn't, it's not perfect doing it this way, but you can say that V plus equals G dt, right? So G times fixed delta time. Okay, and then you can say that V minus equals this value, like BV dt, right? So, and this is your drag constant. Well, we can see here that this has the form V equals V minus BV dt, right? So it's V minus that. So V equals V 1 minus B dt. Now, what I hope you all agree on is that in general it wouldn't make sense for B dt to be greater than 1, right? really you want this value to be between 0 and 1. Because otherwise, the air is pushing you. And okay, that's fine if you've got air blowing, but in general, you don't want your drag to be so high that your static object is experiencing a force from nothing, right? Um, l- Luckily, that just won't happen naturally on its own because it's proportional to when you use the forces, right? When you use this force formula, that will never happen. It drops out. But if you were to do it lazily like this in 2 steps, you could actually accelerate your thing. So you'd always make sure that this is clamped, at 1. And what I've done here is I've made a little simulation that demonstrates that. So you've got an object that's being thrown up in the air and then it's falling, and we can increase the drag here or decrease it. So when we decrease it here, you see eventually it reaches terminal velocity, and well, it won't there because it's got no drag. Okay, you can see I've printed off when it reaches terminal velocity is when there's no difference from the previous frame to the current frame. Go on. Yeah. Up thrust, yeah. Yeah. Well, okay, we'll come back. We're gonna come to that maybe in next lesson. But how we essentially model that is we model water as springs. So you, well, we've not done springs yet, so I'll come back to that. But yeah, that's a good point. But yeah, you can I wish I had more time. We'll just go into this next time in more detail, and we'll talk about what's the difference between this and this. And I call this like quick drag. It's lazy drag, right? And this is a correct calculation for drag. So, and your project, well, I'll just give it you next time as well. But it's going to be to do with drag, so you can start fiddling around with this yourself. But I prefer to fully, teach you before we go into this. I hoped we could get through more today. But to be honest, it's a good thing we didn't get through more today because there's so much physics that we've already got through that if we just speed through everything, we're going to end up in very, very complex territory by the end of the course. We're going to be talking about like inertia tensors and stuff like that, and it's going to be hideously horrifying for everyone. But I'll teach you as much as we can get through. So if we can only get through, less material, then you'll have everything you need to make a like anything you can possibly realistically want to do in a game engine. But if we keep going and we get through a lot of stuff, you'll end up learning some crazy physics. Okay, cool. We're done here. Right. So sorry for the abrupt ending. I'd prefer to plan things that they end on time in general, but I tried to cover too much here. It's too complicated for one lecture.